Hello! Yes! And welcome to our Objective 3.8 notes, our final set of notes for Unit 3. Objective 3.8 says I can solve real-world problems using my knowledge of exponents and logarithms, and that, my friends, is what we're going to do today. So, today is all about using formulas that are either manufactured or that appear naturally in nature, and using them to answer questions. And all of these formulas will be exponential in their nature. So we'll have to use our knowledge of exponents and logarithms to solve. The first formula we're going to look at is the compound interest formula. The compound interest formula is a equals p times 1 plus r over n to the nt. It has 5 variables. Let's go through what those 5 variables represent. A is our final amount. So this is used with money, with currency, with interest. All right, so our final amount is A. P is our principal, which is also known as our initial amount. All right, our principal investment, our initial amount. Then we have R, that is our rate of interest. And it's important that we say that that is written as a decimal because they're generally be given in percent. So we write that as a decimal. N is the number of times compounded per year. So we'll say number of times compounded. So that'd be like if something's compounded quarterly, N would be 4. Weekly, it would be 52. Daily, 365. Monthly would be 12. We get the idea there. T is time. And in this case, it's almost always going to be in years. So let's break down. Let's see what happens when we do some sample problems here. So how long will it take an investment of $2,000 to double if the interest rate is 7% compounded monthly? All right, so let's break this down here. An investment of $2,000, that is our initial amount, to double. Well, that would mean it needs to become $4,000. That would be our final amount, right? Interest rate is 7%, so that would mean my rate, 7% as a decimal is 0.07. Compounded monthly, that means n equals 12. So they're asking how long it will take, so that means I'm solving for t, time. So I'll be solving for a variable in my exponent. So let's go ahead and create the equation that we'll use here. So we'll say 4,000 equals 2,000 times 1 plus r, 0.07, over n, 12, to the 12 times t. Remember, t is going to be what we're solving for. So if I'm solving for t, if I'm solving for a variable in my exponent, first thing I got to do is isolate my base. So I just divide by 2,000. Divide by 2,000. That will give me 2 equals 1 plus 0.07 over 12 to the 12t. And from here, we can create a logarithm. Now, this logarithm is going to be ugly, but that's okay. So it'll be log base of 1 plus 0.07 over 12 of 2 equals 12t. All right, and I just divide by 12 to get t all by itself. So that means t will equal log base 1 plus 0.07 over 12 to the 2, all divided by 12. Now, if we're doing this correctly, we should only use our calculator at the very end. So let's make sure that we're doing that here. Clear out of here. So change of base, I'm going to use a couple parentheses here. I'm going to say log of 2 divided by log of 1 plus 0.07 divided by 12. Close that parentheses. Close the parentheses for the logarithm itself because I'm dividing all of it by 12. When I do that, I get 9.93. So our answer here would be t equals 9.93 years. Voila. Very good. So it would take almost a decade to double your money if you were compounded at 7% monthly. Very good. All right. Let's look at this example here. Compare the growth of an investment of $5,000 in 2 different accounts. One account earns 3%, the other earns 5%, both compounded quarterly over 20 years. So in this case, they just want us to find the final amount. All right, one earns 3% interest, one earns 5% interest. The principal in both of them is 5,000. One plus my rate for this first one would be 0.03. They're compounded quarterly, so that means n equals 4. Over how many years? 20 years, so 4 times 20 in my exponent. So there's one. My other one would be 5,000 times 1 plus 0.05 over 4 to the 4 times 20. So let's put this in our calculator here. So we say 5,000 times 1 plus 0.03 divided by 4 to the up caret. 4 times 20 is 80. I'm just going to go ahead and put that in myself. So one will be $9,090.22 when we round to the nearest hundred. The other would be, let's see if I can just re-enter this and just change this to 0.05, save me some time. Beautiful. The other would be $13,507.42. And there we go. So that's the difference that just 2% of interest makes over 20 years, almost $4,000, over $4,000. Wow. It's pretty awesome. So that's the compound interest formula. Next, we're going to look at the continuous interest formula. Now, the good thing about this is that all of the variables that we dealt with on the prior remain the same. We're just changing it in that we have E involved now, Euler's number, okay? E is involved now. So, how much money will you have after 6 years if we invested $3,500 at a 4% interest rate compounded continuously? So that's the difference here, all right? The difference between the compound interest and the continuous interest is that the continuous interest is consistently occurring. The compound interest occurs a set number of times. The continuous interest is always occurring, and that's why E plays such an important role here, okay? So for this first question, they're just asking us, let's see, what will our final amount be? How much money will we have? So we're going to solve for A. So we'll say A equals my initial amount, P, 3,500. Times e to the r, so that'd be 0.04 times 6 years, okay? So in my calculator, I'll just say 3,500, second e to the 0.04 times 6. And I'll press enter, and I'll get $4,449.37. There we go. Lovely. All right, let's look at this next example. How long will it take an investment of $4,500 to double if the interest rate is 6.3% compounded continuously? So how long will it take? So I'm definitely solving for my t here. So to double, that would be $9,000 if my initial amount is $4,500. So I'll say 9,000 equals 4,500 e to the r 0.063 t. So I'm going to solve for t here. I'm going to have to use a logarithm to do that. But first, I need to get my base all by itself. So I'll divide by 4,500. I'll get 2 equals e to the 0.063 t. And from here, I can create my natural log of 2 equals 0.063 t. Divide by 0.063 to get t all by itself. And I'll find that t equals, in my calculator, I'll put the natural log of 2 divided by 0.063, 11 years. Pretty much on the dot. 11 years to double at an interest rate of 6.3%. All right, not bad. So we've done compound interest. We've done continuous interest. Next, we're going to look at the half-life formula. The half-life formula, half-life is extremely common in looking at chemicals and looking at elements and decay especially. So a lot of these variables remain the same. A is our final amount, P is our initial amount, T is time. H in this case is the half-life value. Now, for those of you who aren't caught up on your chemistry, each element has its own half-life. And the half-life is defined as how much time it takes for an element to naturally decay so that there is half as much of it. So what we're going to do in this first example is figure out the initial amount if after 9,000 years there was 2.1 grams left. So let's go ahead and check out what we have here. The half-life of plutonium, so that would be my H value, 24,100. My final amount was 2.1, and T was the 9,000 years here. So I'm going to figure out what P equals. So I'd say 2.1 equals P times 1/2 to the T, which is 9,000, over H, which is 24,100. Now, this looks really complicated. Like, gosh, how would I solve for P? Remember, P is being multiplied here. To undo multiplication, we just need to do division. So we'll divide both sides by 1/2 to the 9,000 over 24,100. Now, putting this in our calculator might be a little tricky, but we'll try our best. 24,100. So when I do that, I get P equals 2.1 divided by 1/2 to the 9,000 over 24100. In my calculator, I'd say 2.1 divided by parentheses 1/2 to the parentheses 9,000 divided by 24,100. And I'll close that. And I get 2.72. My initial amount was about 2.72 grams of plutonium. Grams. 2.72 grams of plutonium. Wow, that's wild. It's so cool. And that's how they, carbon dating is based in half-life. So many awesome applications here, especially in the sciences. So the half-life of nickel-59 is 76 years. If a substance originally contained 65 grams, how much will it have after 42 years? All right, so this time we want to find the final amount. So we'd say A equals P 1/2 T over H. All right, so 76 years, so that's my half-life value. Originally has 65 grams, so that's my initial. 42 years, there's my time. So let's plug in everything we know here. So we'd say A equals P 65 times 1/2 T is 42, H is 76, and let's put that into our calculator. So we'd say 65 times 1/2 to the parentheses 42 divided by 76, close parentheses, enter, we get 44.32. 32 grams of nickel would be remaining. Very cool. All right. The last formula we're going to look at is population growth. And you're probably saying, whoa, Mr. Carter, P times e to the RT, that was the same as the other, that was our continuous interest formula. You're right. It is. It is pretty much the exact same. The only difference here is the continuous interest generally applies to money, while population growth obviously applies to a population. So let's look at some examples here. In a research experiment, a population of fruit flies increases at an exponential rate. After 2 days, there are 100 flies. After 4 days, there are 300 flies. How many flies will be there after 5 days? So this is a great question because it really makes us think. We're going to solve for the rate, right? We need to figure out the rate first because they don't give us that. They just tell us it's an exponential rate. That's great. And then once we find the rate, we can figure out how many there will be after 5 days. So to figure out that rate, we're going to have to switch some things up a bit. After 2 days, there are 100 flies. After 4 days, there are 300 flies. So we can use that information to figure out our rate. Only I'm going to say that 300 flies, wow, what happened there? All the way back to the top? That's exciting. So 300 flies, sorry about that, is going to be my final amount. So that'll be my Y. So I'd say 300 equals, my initial amount was 100, E to the R, which I don't know. Now, how much time passed between having 100 and 300? That was 2 days, right? So we'd say 2. So I'm going to solve for R here by dividing both sides by 100. 300 divided by 100 is 3. equals e to the 2r. Create my logarithm. So it would be the natural log of 3 equals 2r. Divide by 2, divide by 2. I'm sorry, that says r. Divide by 2. The natural log of 3 divided by 2 is 0.5493. So 0.5493. So that would be 54.93%. That is my rate. Okay, so now that I know that, I can figure out how many there will be after 5 days. But I'm going to, there's a couple ways. I could say my initial amount was the amount after 2 days, or the initial amount is the amount after 4 days, and just do another rate. So what I'm going to do here, just to switch it up, I'm going to say that my 4 days is my initial amount. I'm starting day 4 with 300 flies. I know that the rate is 0.054, oh, sorry, 0. I was like, that can't be right. 0.5493. And then how many days? It'd just be 1 day later, right? Day 5. I want to see how many there are. So in my calculator, I can say 300 times e to the 0.5493. Press enter. 519 flies. 519.61 when we round. So 519 flies. That 521 wouldn't quite exist yet. Fantastic. Wow. Great problem. I love that one. So here's another one that's similar, where we need to find the growth rate, and then we can use that to figure out when the population will reach a certain amount. So let's look at this example here. The population of Hickory was 5,620 in 1992, 8,435 in 2000. What's the annual growth rate? So in this one, we're going to solve for R. So my initial amount, 5,620, that would be my P. My Y would be my final amount, and we have 8 years, 1992 to 2000. So Y is 8435 equals my initial 5,620 times e to the r, which I don't know, and t would be 8. So I'm going to start by dividing both sides by 5,620. 2, 0. When I do that, and notice I'm not going to actually do this math in my calculator yet. Remember, we should only do the math one time. So I'd say 8435 over 5,620 equals e to the 8r. That I can turn into a natural log. So it would be the natural log of 8,435 divided by 5,620 equals 8r. Divide by 8, and I can find what r equals. So I'd say the natural log of 8,435 divided by 5,620, and then divide all of that by 8. 0.0508. 0.0508. So that would be 5.08%, right? Our rates are written in percentages. So if the growth rate remains constant, when will the population of Hickory reach 16,000? Wow, 16,000. So I'd say 16,000 is the final amount. Now, again, I have two options here. I'm going to use this amount here, 8,435, as my initial. And I'll say e to the 0.0508 times t. This time I'm trying to figure out what t equals. Oh boy, oh boy, oh boy. So I do the same process, basically divide by 8,435 to get my base all by itself. So I'd say 16,000 divided by 8,435 equals e to the 0.0508 r. Sorry. That is my rate, 0.0508 t. I'm solving for time. Create my natural log. So I'd say the natural log of 16,000 divided by 8,435 equals 0.0508 t. Divide by 0.0508. Let's put that in our calculator. So the natural log of 16,000 divided by 8,435, and then divide that by 0.0508, you get 12.60. So t equals 12.60, but think about that. That's not saying the year 12. This is 12 years after our initial. So our initial was from 2000, so that means 2012 would be my answer here. All right. Now, the last type of problem you might see is one where they give you the equation. So for this last problem, they give us the equation, and there's that apparently. Put this back up here. And then it's your job, our job, just to plug in values, see what happens here. So educational psychologists sometimes use mathematical models of memory. Suppose some students take a chem test after a time t in months. Without a review, they take an equivalent form of the same test, the mathematical model here. A is the average score at time t is a function. Oh, cool. So it's what they retain. What is the average score when the students first take the test? T equals 0. Okay? So I'd just say A of 0 equals 82 minus 12 log of 1. Okay, well, that's going to be 0, so this is going to be easy. 82 minus 12 times the log of 1. Hey, what do you know? It's 82. So 82 is the average score. What's the average score after 6 months? So that would be A of 6. I'd plug in 6 for T. So 82 minus 12 log of 6 plus 1, which is 7. So I'd say 82 minus 12 log of 7, 71.86. And then, after how many months is the average score 60? Oh, okay. So the average score, why is it doing this? I've been working it so hard. The average score, remember, is the A, so that's what we're going to find. We want 60 to equal 82 minus 12 log of some number of months, t plus 1. So we're going to have to solve this, aren't we? So we subtract 82 from both sides. We get negative 22 equals negative 12 log of t plus 1. Divide by negative 12, divide by negative 12. When I do that, I'd get 22 over 12 equals the log of t plus 1. Let's convert that. So it'd be 10 to the 22nd over 12 equals t plus 1. And subtract 1 from both sides. So t will equal 10 to the 22nd over 12 minus 1. So let's do our math here. 10 to the up caret 22 divided by 12, and then minus 1. T will equal 67. So 67, goodness, 67 months. Wow. So once you know it, man, you're going to retain that thing for like 5 years before you get a failing grade. That's pretty wild. All right. Hopefully we're feeling confident with these exponential applications, exponential and logarithmic applications. We went through a ton today. Great math at work here. If you want to see some more sample problems, go ahead and check out that video. If you're feeling confident in what we've done, go ahead and get started on those practice problems, see how you do on your own. Hopefully we're feeling good. As always, if you have questions, reach out. Otherwise, this is Mr. Carter signing off. I'll see you next time.